I think will be Yuyao, right? Yes. Okay, great. So let me first do the introduction. Yuyao is currently a second-year master student in computer science in China University of Petroleum, Beijing, and is planning to pursue her PhD after graduation. Her advisor is Professor Weifeng Liu. Her research interests include high-performance computing, parallel programming, parallel algorithms, and sparse matrix computation. So, Yuyao, please start your presentation from beginning. And I'll give a timing reminder at around 12 minutes.
Okay. Hi, everyone. Can you see my screen?
Yes, please go ahead.
Okay. Hi, everyone. I will introduce our new method of optimizing parallel sparse matrix vector multiplications on GPUs, named TileSpMV, and our co-authors are Zhiyang Lu, Meichen Dong, Dr. Zhou Jing, Dr. Weifeng Liu, and Dr. Guangming Tan. So I will introduce our research from these four aspects, and let's start with the background and our motivation. Sparse matrix vector multiplication multiplies a sparse matrix A with a dense vector X and gets a dense vector Y. So the figure below shows a very simple example of a 4x4 sparse matrix, and as we can see, the yi is computed by the dot product of the ith row of A. And SPMV plays a very important role in many applications of areas, and it may be the most studied kernel of the level 2 sparse bus in the past decades. Despite lots of attention and research, and the existing SPMV work still has three challenges. And the first one is about the optimization of detail locality and the reuse of X. And the work of sparse system in 2004 have proven that the reuse of matrix A and vector Y cannot be improved, but the reuse of vector X can be optimized if there are elements in A that are in the same column or nearby one another. So they store a sparse matrix into a sequence of dense blocks to improve the detail locality and the reuse of X. And secondly, the most existing work focus on the optimization for the very sparse matrices. However, there lacks SPMV implementations optimized for very small sparse matrices that can be stored in the on-chip scratchpad memories. And the third one is about the microstructure of a sparse matrix using machine learning. So although the format and algorithm selection techniques using machine learning or other methods are effective in SPMV, they have only been used for the whole matrix, but neglect the microstructures of a sparse matrix. So according to the above three challenges, we proposed our tiled algorithm named TileSpMV. Our TileSpMV first divides an input matrix A into a number of sparse tiles of the same size and use a sparse tile as a basic working unit. So the figure shows a compressed sparse matrix A of size 16 by 16 are stored as 10 sparse tiles of the size 4 by 4. And after the partitioning, two levels of information are generated for storing sparse tiles. And the first level stores the tile structure of the sparse matrices, and the second level stores the internal information of each sparse tile. And in this work, we provide 7 options, and each format has several corresponding arrays to store the the values and indices in it. And then in order to better compute the sparsity structures of the tiles for SPMV, we developed 7 corresponding WAP level SPMV algorithms for different formats. And we assign a WAP of 32 threads to deal with a sparse tile in our of size 16 by 16 in our work, and use the different threads allocation according to the different the sparsity structures of sparse tiles, and correspond to the figure of size 4 by 4 sparse tiles. We assume that we have 8 threads to deal with the sparse tile, and take CO tile as an example. We only use 2 threads to process a CO tile because, as we can see, there are only 2 elements in a CO tile. So also we have different optimization strategies for our CSR, dense row, dense column, LPAC, HYB, and dense SPMV algorithm to reach the better performance. And on top of the storage structure and basic 7 WAP level SPMV kernels, we implement 3 TileSpMV algorithms here. TileSpMV CSR method, TileSpMV adapt method, and TileSpMV defer CO method. And the first one, TileSpMV CSR method, always store all the sparse tiles as the standard CSR format. So it is very simple. So we directly introduce our second version, TileSpMV adapt method. And TileSpMV adapt method inspects the sparsity structures of each sparse tile, and then adaptively selects a format from the 7 to store and calculate the sparse tile. And we design a 2-level selection method to automatically find the most suitable format and algorithm for each tile according to its sparsity structure. And we firstly select these 4 formats: CO, dense row, and dense column, according to the number of non-zeros in each sparse tile. And then the standard of the second level is the distribution of non-zeros in each row in sparse tile. And we use the parameter variation. That's the ratio. That's the ratio of standard deviation to average row length to evaluate the balance of non-zero distribution. And we set 2 thresholds here, TE and TH, to distinguish the remaining 3 formats. And our experimental data shows that when the TE equals 0.2 and TH equals 1, our performance can reach the best. And we further propose the third version, TileSpMV defer CO method for very sparse matrices. And in this method, we all the CO data, including the tiles in CO format and the CO part in HYB format, are extracted to form a separate matrix and stored as a normal CSR format. And this matrix is computed by the CSR5 SPMV, and the remaining matrix still called the TileSpMV adapt method. And the second part, our experiment. Our experimental platform includes two NVIDIA GPUs, GeForce Titan RTX GPU of Turing architecture and latest Ampere 100 GPU of Ampere architecture. And we compare our TileSpMV work with the latest Sparse version 11.1 using BSR format. The merge SPMV algorithm proposed by Merrill and Garland, and CSR5 SPMV algorithm proposed by Liu and Winter. And our dataset includes all sparse matrices in the sparse matrix collection. And we first plot the ratio of tiles in different formats and the ratio of non-zero entries in different formats. And the different color bar present different formats. So as we can see, even though there are many tiles in the zero format, the number of non-zeros of zero format is not very high. So because the low density of the zero format. So store zero data as a tile and use a WAP of 32 threads to deal with them can be a choice of wasting computational resources. So that insight gave us a thought to continue optimize our TileSpMV adapt method. And we compare our three versions of Tiles algorithm, Tiles SPMV CSR, TileSpMV adapt, and TileSpMV differential. And that's the performance, comparison, and the speed up. As we can see after the format selection, the performance of TileSpMV adapt can be 6.75 faster than the TileSpMV CSR. And as we can see, the advantages become more obvious as the size of matrices increase. So when the size of matrices is relatively small, we continue to choose the TileSpMV adapt method. But when the size is larger than a certain size, as we can see 1.8 million in our work, the advantages of TileSpMV differential begins to become prominent. And it can further achieve up to 7.02 speed up than TileSpMV adapt. And we compare our TileSpMV with the merge SPMV CSR5 and BSR work. And as we can see, compared with these three methods, our method is faster than merge SPMV about 1,800 matrices, faster than CSR5 on 2,040 matrices, and faster than BSR on more than 1,600 matrices. And it can be seen
Sorry, finish 1 minute left.
Okay.
Yeah.
our method is very effective in most of common used matrices. And that's the memory cost comparison of our CSR and TileSpMV CSR and TileSpMV adapt. And finally, we can make a conclusion of our of the presentation. And we propose an effective TileSpMV method and propose design optimized web-level SPMV kernels and design an adaptive selection method. And the experimental data shows our method is very effective on most of the sparse matrices. And that's all. Thank you very much for your attention.
Thank you for the presentation. So let's give a pause. And please type any question if you have anyone in the chat window, or unmute yourself to ask that. So we have maybe just 1 or 2 questions for this talk.
I have a question. Can you hear me?
Yes, please.
For your optimized tiled sparse matrix vector multiplication, where do you make the decisions? Is it on the CPU or on the GPU for choosing the multiplication method?
Our work is implemented on GPUs.
So the choice of algorithm for the choice of the data structure that is made, choice is made on the GPU.
Yeah.
And how much time does it take for you to decide which method to choose? That is, what is the tile? That is, which tiling method to choose? Whether to use the adaptive method or COO or CSR.
Yeah, so the question is about how much time do you need to choose between different format, different like CSR versus adaptive or what in the adaptive method?
Oh, it's a
Go ahead.
question about the pre-processing time.
Yes, yeah, kind of. Mm-hmm.
The figure. We plot these figures and talk about it in our full presentation in 25 minutes presentation.
Yeah, so please maybe if you have the answer, please type it in the chat window, or if you don't have it at the top of your head now.
Yeah, I'll check the paper if it's not in the presentation.
Okay, thank you.
Okay, thank you.
Thank you. So I think maybe we need to move to the third talk. And sorry, there is another question in the chat window asking about the shared memory size. So, Yuyao, can you respond to these two questions in the chat window as well? And then we'll move on to the third talk. Is that okay for you?
Yeah.
Okay. Thank you for your presentation.